In this video, we will explore a progressive mathematical framework for understanding the electromagnetic. This presentation will take us from classical electromagnetism, governed by Maxwell's equations, to a more sophisticated tensor and differential geometry-based approach. By the end, we will have a deep understanding of how these mathematical tools coherent, scalable, and quantum-informed model of electrodynamics. We start with the foundation mathematical representation of electromagnetics, which is based on vector calculus. In this view, Maxwell's equations includes 4 equations. The first equation, Gauss's law for electricity, states that the divergence of the electric field is proportional to charge density. The second equation, Gauss's law for magnetism, magnetic field lines are always closed, implying that there are no magnetic monopoles. The third equation, Faraday's law, describes how a time-varying magnetic field generates an electric field, forming the basis of electromagnetic induction. The fourth equation, Ampere's law, with Maxwell's correction, states that a changing electric field kinetic field. These equations provide the backbone of electrodynamics. They are expressed in a coordinate-dependent way based on gradient, divergence, curl, Laplacian formulations. Gradient measures the rate of change of a scalar field, such as electric potential. Divergence describes how much a vector field spreads out from a point, crucial for Gauss's law. Curl tendency of a vector field, fundamental for Faraday's law. And Laplacian is essential for solving field equations in space. Vector calculus representation of electromagnetism has several advantages. It is used for dimensional transformation as shown in this slide. They can convert line to surface and the surface to volume. In addition, one of the most powerful techniques in electromagnetism is Helmholtz-Hodge decomposition, which states that any vector field can be decomposed into a divergence-free, solenoidal component, describing conserved fluxes, a curl-free, irrotational component, which represents potential-driven fields, and a harmonic component, capturing long-range interactions. This decomposition is especially useful for analyzing how electromagnetic fields behave in complex, non-uniform brain. However, vector calculus is limited in expressing field interactions in curved and higher-dimensional spaces. This is why we move toward tensor calculus. The electromagnetic field based on vector calculus expressed by wave equation, which is working with E and B fields directly, is instead of E and B fields. In next level we introduce the 4-potential mu, which simplifies the description of electromagnetic fields in a relativistic framework. This representation also sets the stage for integrated dynamics. In this point of view, the scalar electric potential and vector magnetic potential is integrated in single covariant 4-vector, which is demonstrated as tensor graphical representation. By this transformation, the other parameters like current also can be integrated into the contravariant vectors. To address these complexities, in the next slide, tensor calculus, which generalizes these operations into a framework that is valid in any coordinate system. In this slide, we introduce tensor calculus, which extends vector calculus to higher dimensional and curved spaces, providing a more general framework for describing electromagnetic fields in complex geometries. This is crucial for understanding electromagnetic interactions in the brain, where structures are highly non-Euclidean and anisotropic. In tensor calculus is the covariant derivative, which allows differentiation in curved spaces while preserving geometric consistency. Unlike ordinary derivatives, it accounts for spatial variations and curvature, ensuring that electromagnetic fields transform correctly under coordinate changes. The Levi-Civita connection, defined by Christoffel symbol, vectors change as they move across a curved manifold, which is essential for modeling electromagnetic wave propagation in biological tissues. To analyze electromagnetic forces in material media, we use the electromagnetic stress-energy tensor, T-mu. This tensor captures the energy and momentum distribution of electromagnetic fields, field interactions with matter. In biological tissues, where dielectric properties vary, this tensorial approach is necessary to describe electromagnetic forces, wave propagation, and stress distributions within the medium. Additionally, the stress tensor helps visualize the mechanical forces induced by electromagnetic fields. The rank 3, dimension 3, encodes force distributions in all directions, revealing how electromagnetic fields interact with complex biological structures. By using tensor calculus, we ensure that these interactions remain consistent across different coordinate systems, making it a fundamental tool for studying electromagnetic processes in the brain and other biological. In this slide, we explore the covariant formulation of electromagnetism, which unifies electric and magnetic fields into a single electromagnetic field tensor. Unlike classical approaches that treat these fields separately, this tensor ensures that Maxwell's equations hold in any reference frame, making them consistent under Lorentz transformations, flat and curved spacetimes. By using this tensorial representation, we simplify field transformations and gain a deeper understanding of electromagnetic interactions in complex geometries, including biological tissues and high-energy physics applications. Maxwell's equations take an elegant form, with the Gauss-Ampere and Faraday laws revealing fundamental symmetries of the field. Beyond describing field evolution, the electromagnetic stress-energy tensor provides a way to analyze energy and momentum transfer within electromagnetic fields. It governs forces exerted by fields on matter, playing a key role in understanding radiation pressure, wave momentum, and stress in different media. The Maxwell stress tensor further helps quantify how electromagnetic forces interact with materials, ensuring a precise formulation of field dynamics. This geometrical approach allows electromagnetism to be seamlessly integrated into relativity and spacetime curvature, making it a crucial tool for studying plasma physics, magnetism, and electromagnetic interactions in complex biological systems. By adopting this formalism, we achieve a more general and robust understanding of electromagnetic phenomena across a wide range of physical environments. In this slide, we introduce a coordinate-free approach to differential geometry, which extends classical vector calculus to a more generalized framework. Traditional differential operators such as gradient, divergence, and curl depend on a specific coordinate system, making them less adaptable to arbitrary geometries, curved spaces, and higher dimensions. To overcome this limitation, we use differential forms and exterior derivatives, which allow us to express physical laws independently of coordinates. This shift to a coordinate-free formalism is particularly powerful in electromagnetism, relativity, and field theory, where fields often exist in complex, non-Euclidean spaces. The gradient to measure local changes in a function, we use the exterior derivative of a differential form. Similarly, divergence and curl are replaced by exterior derivatives acting on vector fields or differential forms, ensuring that fundamental equations remain valid in any geometric setting. The Hodge-Laplacian further extends these operators, realization of the Laplace operator that naturally applies in curved spaces. By adopting this perspective, we gain a more flexible and universal framework for analyzing physical systems, particularly in cases where traditional vector calculus breaks down. This is essential for studying electromagnetic interactions in complex biological structure, geometry and relativity, and wave propagation in anisotropic media. Transitioning from coordinate-dependent to coordinate-free formulations allows for a deeper understanding of field dynamics, geometric structures, and fundamental physical interactions in both theoretical and applied. Continuing from the previous slide, we now explore how classical vector calculus concepts such as gradient, curl, divergence, and Laplacian translate into differential geometry using exterior derivatives. The goal is to develop a coordinate-free approach, ensuring that these fundamental operations remain valid in arbitrary geometries and curved spaces. With the gradient, which in traditional vector calculus measures the rate of change of a scalar function. In differential geometry, this is replaced by the exterior derivative, which acts on a zero form, a scalar function, and produces a one form that represents infinitesimal changes without depending on a specific coordinate system. This generalization expresses field variations in a fully geometric manner. Next, we replace the curl with the exterior derivative of a one form, which naturally extends to the Faraday 2 form. This transformation removes the dependence on predefined coordinate systems, making it applicable in generalized manifolds and high-dimensional spaces. By using differential form, computational field behavior in a way that remains consistent under coordinate transformation. Similarly, the divergence of a vector field is reformulated using the exterior derivative of a dual form. Instead of relying on dot products in Cartesian coordinates, this approach introduces the Hodge-star operator, which maps between different degrees of differential forms. This perspective ensures that divergence remains well-defined in anisotropic and curved space, making it highly useful in physics and engineering applications. Finally, we extend the Laplacian, which in classical vector calculus describes diffusion and wave propagation, to the Hodge-Laplacian. This generalization combines the exterior derivative, codifferential, and Hodge-star operator, creating a powerful framework for describing differential geometry. By adopting the Hodge-Laplacian, we gain a deeper understanding of wave behavior, potential theory, and harmonic analysis in curved and high-dimensional spaces. By transitioning from classical vector calculus to differential geometry, we establish a more flexible and universal mathematical framework for describing physical fields, which is essential for electromagnetism, fluid dynamics, general relativity, and quantum field theory, where fields evolve in complex and non-Euclidean spaces. Moving forward, this perspective allows us to analyze electromagnetic wave interactions, geometric field effects, and topological structures in ways that transcend traditional coordinates. In this slide, we reformulate Maxwell's equations using the language of differential forms, making them coordinate-free and compact. Instead of expressing electric and magnetic fields as separate vector quantities, we describe them using differential forms, exterior derivatives, and Hodge duals. This approach not only simplifies the equations, but validity in curved and arbitrary geometries, making it a powerful tool in relativity, electromagnetism, and field theory. Maxwell's equations reduce to two fundamental expressions in this formalism. The first, dF equals 0, encodes the homogeneous Maxwell equations, Faraday's law of induction and the absence of magnetic monopole, that the exterior derivative of the Faraday 2 form F vanishes. The second equation, d** operator F equals J, represents the inhomogeneous Maxwell equations, relating the Hodge dual of the field strength tensor to the current 3 form J, which accounts for charge and current densities. In this framework, the electromagnetic field strength Faraday 2 form, F equals d, where A is the electromagnetic potential 1 form. The current density is described as a 3 form, ensuring conservation laws remain consistent across spacetime. The Hodge dual *F plays a crucial role in defining the displacement field, allowing us to extend electromagnetism naturally into curved manifold settings. By transitioning to this geometric formulation, we gain a deeper insight into electromagnetic field behavior, particularly in non-Euclidean spaces and high-dimensional theories. This approach provides a more elegant and flexible representation of electromagnetism, enabling its integration with general relativity, quantum field theory, and topological. In this slide, we introduce the gauge theory perspective of electromagnetism, which plays a fundamental role in both classical field theory and quantum electrodynamics. Unlike traditional descriptions of electromagnetic fields, where the vector potential mu is treated as a physical entity, gauge theory reveals that this potential is not uniquely transformed without altering the measurable electromagnetic fields. This property, known as gauge freedom, allows us to shift mu by the gradient of a smooth function without changing the electric and magnetic fields. This means that while mu itself is not directly observable, the Faraday tensor F mu, which encodes both E and B, remains gauge invariant. This reinforces the idea that only the field strengths, rather than the potentials themselves, carry physical significance. From the perspective of differential geometry, the electromagnetic field strength tensor F mu is not merely a vector field but rather the curvature of the gauge field mu. In this formalism, electromagnetism can be seen on a principal fiber bundle, where the curvature of this connection gives rise to the physical field. The integral formulations illustrated here show how different gauge choices affect the way fields are interpreted in different regions of space. This gauge-theoretic formulation is the foundation of quantum electrodynamics and extends to other fundamental forces in the standard. Interactions are mediated by gauge fields. By adopting this perspective, we see that electromagnetism is not just a force, but a manifestation of underlying geometric and topological structures, making it a key example of how gauge symmetries shape modern. In this final slide, we bridge quantum electrodynamics, gauge symmetry, and Lorentz symmetry to the fundamental equations of electromagnetism. Electromagnetic interactions are governed by local U1 gauge symmetry, which dictates the behavior of the electromagnetic field as a gauge field. The quantum field psi/psi, particle, transforms under this symmetry, ensuring the invariance of physical laws under phase shifts. This local symmetry introduces the gauge connection mu, which interacts with the charged field through the covariant derivative, defining how the electromagnetic potential evolves in spacetime. From Noether's theorem, this gauge invariance leads to the conservation of charge, ensuring that charge is a fundamental conserved quantity in nature. Charge conservation is expressed through the continuity equation, which, when integrated over space, directly links to Gauss's law and the structure of Maxwell's equations. The field strength tensor F mu, defined through the commutator of covariant derivatives, encodes the electron components and follows the Bianchi identity, ensuring consistency with Maxwell's equations. On the Lorentz symmetry side, we extend this formalism to relativistic spacetime transformations. The Dirac field psi transforms under the Lorentz group representations, incorporating spinor fields into electrodynamics. The Euler-Lagrange formula emerges, describing how charged fields couple to the electromagnetic potential. By applying the quantization process, we derive the fundamental force laws governing charged particles, leading to the Lorentz force equation, which describes the motion of a particle in an electromagnetic field. Ultimately, this framework unifies classical electromagnetism theory, showing how Maxwell's equations, charge conservation, and the Lorentz force law arise naturally from deeper symmetry principles. By understanding electromagnetism as a gauge theory, we establish the foundation for modern particle physics, connecting classical fields, quantum interactions, and relativistic dynamics into a single. In this presentation, we explored electromagnetism through the lens of differential geometry, gauge theory, and quantum electrodynamics. We saw how Maxwell's equations emerge from gauge symmetry, how the electromagnetic field tensor is fundamentally linked to curvature, and how charge conservation, Lorentz symmetry, and quantum field theory unify quantum electrodynamics. In the next video, we will extend these mathematical representations to quantum neuroelectrodynamics and explore how electromagnetic fields in the brain can be described using quantum electrodynamic principles. This will allow us to analyze the role of electromagnetic waves, quantum coherence, and neurodynamic interactions. Stay tuned as we take the next step into the electromagnetic nature of consciousness. This unified mathematical framework provides a robust foundation for studying electromagnetic brain activity and its interactions with neural structures. As we advance our research, we can further explore how electromagnetic fields influence cognition, brain function, and inspired models of consciousness. Thank you for your attention.